So today we're going to discuss inverse functions. As part of our discussion, we want to learn exactly what is an inverse function, when can we find inverse functions, and how do we find inverse functions. And then we're also going to look at the relationship between functions and their inverses. So we have lots of ideas to discuss in this section. Now, well, before I continue, notice I have some writing here already. That's because I keep getting interrupted with my video. I'd already started it and I have to start over, so I'll explain this when I get to it. But let's go back to the beginning here. So I just kind of started off talking about just informally what does it mean for a function to have an inverse. And so remember, a function gives us our rule. It tells us what to do to an input. So in this first example, I have f at x is 3x plus 2. And so what we want to do when we find the inverse of this, if there is an inverse, is undo those operations. We have an operation of multiplication by 3 and then addition by 2. Well, how can we get rid of that addition by 2 and multiplication by 3? And it's kind of like solving an equation. You know, what would you do to get x alone, basically? You need to reverse the order of operations. And so since we multiply first and then add, to undo this, we're going to need to take away the 2 and then divide, as we'll see, and we're going to write the function. But I'm getting a little ahead of myself here. Let's go back here. So what I did here, I started off with an example of an input and an output. So I said, well, let's use 0 as an example. And again, we can never prove by example, but examples are nice to help with our understanding sometimes. So this example isn't going to prove that we get the true inverse, but it's going to help us understand the inverse. All right, so I plugged in 0, and of course 0 operates on x and we get out 2. So f takes the input 0 and maps it to 2, right? Input, output. Now the inverse, and this notation here is likely new for you. This means f, the inverse of f. It does not mean an exponent. This does not mean 1 over f, okay? Not an exponent in this case. It's just notation to represent the idea of inverse. So if our function is g, we'll write g to the -1, and that's read g inverse. Alright, so back to this. This function operated on 0, got out 2. What we want the inverse to do is undo that. So if we plug in this output 2, it's going to bring us back to where we started, which was 0. Okay, well we can write, because this is a pretty basic function with just 2 operations, it's pretty easy to come up with what we need to do. Now, we want to be able to do this in general, not just for 2, right? Or sorry, for 0. No, 2, I said that right. When we plug 2 into f inverse, we want to get out 0. So think about this 2. What would you have to do to get back to 0? Well, since when we plugged in 0, we multiplied by 3 and added 2, we're just going to reverse that. So it would be 2, and then we would take away the 2, and then we would divide the 3. That would give us our 0. Well, now just use a placeholder in place of this. Instead of doing it for a specific 2, do it for x. X minus 2 over 3. And now this is the true inverse. We'll talk more about how you can tell if you have the true inverse a little bit later. For now, just take my word for it. But no matter what number I put in here and get out an output, if I take that output and put it into this formula, I'm going to get back to the original input. So for example, let's do a different number. F at 10 is 32, right? 3 times 10 plus 2. And f inverse at 32, notice 32 minus 2 is 30, and then divide by 3 is 10. So in any example I come up with, this is going to work. Input to output, and then that output brings it back to the input. So what ends up happening with the function as inverse is every set of ordered pairs that you have on the graph of f, those are going to just be inverted, and those will make up the graph of f inverse. So that's our first relationship, and we're going to talk more about that. But when you have a function, all of the ordered pairs on the function, if that function has an inverse, that inverse is made up of all of those ordered pairs inverted. And I actually wrote that down right here, so you don't need to write that down. Okay, but more formally, this would be the more formal definition of the inverse. And don't be confused by the notation, it's not that complicated. This is just saying that, you know, if we do have this inverse, and not every function has an inverse, we need to keep that in mind. But if we do have an inverse, that when you plug in a number into the inverse, right, this is the input into f inverse, you know, here's your output out of f inverse. You plug that output into f, and it undoes f inverse and brings you back to the input of f inverse. So notice this is just f undoing f inverse. So f actually undoes f inverse, and f is the inverse of f. Oh, sorry. I don't even know if I said that right. It all sounded too much the same. F is the inverse of f inverse. Okay, notice this is composition, so we could also write this f composed with f inverse at x. Likewise, here we have the input, you know, into f, right? And then you get your output f at x. Now when you plug that into f inverse, it undoes it, brings you back to the input. That's all that's really saying. And again, this is composition, f inverse at f at x. Now I used the inverse notation here. You could say f and g, and then this would say f composed with g at x, and g composed with f at x. The notation doesn't matter. What matters is what's actually happening in the composition, that these things are undoing each other and bringing you back to the original number, the original input. We can draw a picture to represent that using the circles to represent this domain and range for our sets, and the idea of the mapping. So say we have the domain of f, and you've got everything in here would be in the domain of f. F operates on x, and you get out f at x. And then this set collection of, you know, all of the function values would be the range of f. So this output, if you plug it into the inverse, brings you right back to where you started. There's f inverse. And so notation-wise, we can say f inverse at f at x. And that gives us actually the second equality in our definition. But this equality, you can come up with this one by, it's a little confusing because you get so much embedding into parentheses. So what I want to do is you want to think of this as your starting point instead of this. So this number, let's just call it y instead of f at x. Okay, so we have this number, and we're going to plug it into f inverse. Well then, what we would get is f inverse at y. And then when you so use this instead of this when you're plugging into f. You know, that's what I meant by so much embedding this at this. It gets confusing. So use this instead, because of course we know y is f at x, right? So f at f inverse at y. Notice that's basically this statement here, just with y's instead of x's. And that's just a placeholder. It doesn't matter if you really call, you know, what you call it. Think of it as just a empty spot for your input. The key is the pattern is there. So you can, from this diagram, come up with this equality as well. And the other thing that we want to notice here is if we're thinking of this as our start, as our domain, it's the domain of f inverse. and that's going to be exactly the range of f. So with inverse functions, these two sets have to equal, and then this ends up being the range of f inverse, and that's going to equal the domain of f. So this relationship will always hold. And if it doesn't, then we need to either throw out the inverse function, or we can make an adjustment. And we're going to talk more about that in a little bit. I'm going to myself when I say that. All right. In this example, it says find the inverse of each function if it exists. Okay, so this, we keep talking about how the function may or may not even have an inverse. So here we don't have a rule like we did in the first example. We just have sets of ordered pairs. And so this function f, takes 5, and we don't know what rule it is, but we know it will bring it to 6. It takes 9, and it will bring it to 2. It takes 8, and it will bring it to 0. So the inverse should reverse that. If you plug 6 into the inverse, it should bring it back to 5. Plug 2 in, bring it back to 9, 0, back to 8. And the function, that's fine. That gives us a function, and so f inverse does exist. And it's just going to be all of these ordered pairs inverted. Okay. So the if it exists part, where that comes into play, is you need to make sure that if you are going to invert these coordinates, because you can always take, function defines ordered pairs, you can always invert the coordinates. That's no problem. The problem is going to be if once you do that, is this result a function? So notice with g, if we invert these, -2, 3, -2, 4, 5, 2, this is not a function. And so I don't even want to call this g inverse, because I can't use function notation if I don't have a function. This is just a relation, and we won't use function notation. What we can say is g inverse does not exist. All right, well, in a more complicated function, we don't want to actually have to invert everything before we know whether or not we'll get a function from that process. And so what we can do is check first if the function is what we call one-to-one. And one-to-one means that when you have your output and you look back to the input, it's only going to correspond to one input. So one input to one output. 1-to-1 both ways. The function part ensures that the input goes to one output, and then the 1-to-1 part ensures that output only goes to one input, corresponds to one input. So notice in the function g, if I do the mapping here, you've got 3 goes to -2, 4 goes to, -2 is the same number, so we don't write it again. Draw an arrow pointing to -2, and then 2 to 5. This right here, you've got the 2 going to 1. So when you look back, if you invert this, you're going to have the 2 -3 and the 2 4, and that's when it's going to fail to be a function. You've got 2 going to 1. So here, each output corresponds to exactly one input, not 2 or more inputs. Okay, so we need the function to be 1-to-1, and then we'll know that it's invertible. So we're going to check for this rather than invert all the coordinates first. Okay, we're going to check for whether or not the function is 1-to-1. Okay, so this theorem here just sums up what I just said. but let me discuss this here for the if and only if. So it says a function is invertible if and only if it is one-to-one. And by being invertible, we mean the inverse exists, right? All right, so the if and only if means that basically that being invertible is equivalent to being one-to-one. You can't have one without the other. So you can say a function is, if a function is invertible, then it is one-to-one. You can also say if a function is one-to-one, then it is invertible. Let me write that down. So if invertible, then I'll just abbreviate one-to-one like this. And then if one-to-one, then invertible. It goes both, the if-then statement goes both directions. In notation, you'll see a double arrow. The if-then, would be written this way. The double arrow means it goes both ways. So being invertible and being one-to-one are basically equivalent. You can't have one without the other. You'll never have a one-to-one function that's not invertible. You'll never have a function with an inverse that's not one-to-one. And whenever you find an inverse function, its inverse is the original function you started with. In other words, the two functions are inverses of each other. So they both need to be one-to-one. And that's something we'll discuss some more in a little bit. We need to make sure both functions are one-to-one. All right, well, we want a quick way to check for a function being one-to-one. If you understand those basic graphs that we talked about in the transformations, then using the horizontal line test will be the quickest way to tell if a function is one-to-one. And what this will test, it basically works like the vertical line test. So let me write it down. If every horizontal line, I don't know why I didn't type this, sorry, crosses the graph of a function at most one time, then that function is one-to-one. All right, so our assumption is we're starting with a function. So this already, we know this passes the vertical line test. That's implied. Okay, so we're not doing this for anything that wouldn't pass the vertical line test as well. And the reason this works, like if you look at the 3, the function that was not invertible. Sorry, I was looking at after we inverted. I should have put in 3, -2. Okay, so 1, 2, 3, 1, 2. And then 4. Well, that's going to be in the way, so I'm going to move it. 4, -2 is here. And then 2, 5. Of course, that's not the one that fails, so that's up here. But notice, because these have two different inputs going to the same output, they line up horizontally, and that's why the horizontal line test will work. It'll if you hit any the graph 2 or more times anywhere, then it's not one-to-one. That'll be a quick test. Now there's going to be let's just leave it like as that for now. Let's move on. Okay, so here's what we know so far. Here's what Here's what we know so far. That if f is invertible, then we know the relationship about the graphs, that if AB is on the graph of f, then we know that BA is on the graph of f inverse. And because they're inverses of each other, it goes both ways, and that's why we have if and only if then. We also know that because they're inverses of each other, both of these functions have to be one-to-one. And then we talked about the domain of f being equal to the range of f inverse. range of f equals the domain of f inverse. And we talked about this statement as well, that these compositions, both orders, the operations undo each other and you get back to the beginning x. And then we're going to add a number 6 a little later. We're going to come back to that. Okay, so in this example, I've got two functions. One's called f and one's called g. We would like to prove that these are inverses of each other. Now these functions, we haven't talked about these types of functions yet. We're going to talk about them. I can't remember if it's chapter 3 or chapter 4, but at any rate we will. But for now, the only thing we're going to do to show that these are inverses is that it satisfies the definition. And remember, the definition said that these operations will undo each other. Okay, if they're not one-to-one, this isn't going to happen. If one of them's not one-to-one, so we don't even really need to worry about that part of it to prove this. We just need to show this. Okay, so f composed with g at x is f at g at x. Okay, let me write this down. So we need to show f composed with g at x equals x and g composed with f at x equals x. You need to show both directions. Sometimes one function will undo one, but then if there's something wrong with something not being one-to-one, then the other direction might not work. So you have to be careful and make sure you show both. Okay, once I show these are inverses, I might change this notation to f inverse notation. Okay, so f at x over 2 minus x. So this thing here is going in place of these x's. We get 2 times x over 2 minus x divided by x over 2 minus x plus 1. Alright, and that yields a complex fraction, which might seem a little overwhelming at first to simplify this. But the easiest way to simplify a complex fraction is to look at this as one fraction here and then say, what is within this numerator and this denominator, what's the LCD of all the little fractions that you see in there? And that LCD is 2 minus x. So we're going to take this top times that LCD 2 minus x and this bottom times that LCD 2 minus x. And when we distribute, that's going to clear the fractions. But you have to make sure you distribute correctly. Now this, don't take this times 2 and this times this, because this is multiplication. This 2 is really just on top here, okay? So we can cancel the 2 minus x, and we just get 2x on the top. On the bottom, we distribute through addition or subtraction. So you need to take this times 2 minus x and the 1 times 2 minus x. So the x over 2 minus x times 2 minus x is just going to be x. And then plus 1 times 2 minus x. And notice that x minus x is 0. So we've got 2x over 2. Those cancel. And we do get back to the original value of x. Okay, so this is a proof here. And we did the first half. Sorry, I gotta make sure I'm not writing off screen, and I am. This is the first half. The second half, so there's part 1. We need to reverse the order of composition and show that g also undoes f. And this is going to work very similar to part 1. So we've got g at f at x is g at 2x over x plus 1. Alright, so this time, erase all of this. We're going to take this thing and plug it into these x's. So 2x over x plus 1 in the numerator over 2 minus 2x over x plus 1. Okay, so again, a complex fraction. Look at that big fraction, look at the terms in there. What's the LCD of these little guys? well, it's x plus 1. So we're going to take the top times x plus 1 and the bottom. And of course the reason that's okay is because x plus this divided by this is 1. So it's like multiplying by 1. These cancel. We just get 2x. This is this over this. 2x on the top. And then distribute through 2 times x plus 1 minus, and then these x plus 1's cancel and we just get 2x. So now we've got 2x over 2x plus 2 minus 2x. That adds up to 0. 2x divided by 2 is x. And so that's what we wanted to get. We wanted to show that we could break, you know, that everything would get undone and we get back to x. That's the original, right? And so when you show both of these equal x, so since f composed with g at x equals g composed with f at x, you've shown they undo each other and equal x, then you can conclude f and g are inverses. So that means they're inverses of each other. Okay, so that we didn't use inverse notation. That's okay. You don't have to. But if you did, it would just change all the g's to f inverse. All right. I think this is a good place to take a break, and then we're going to talk about actually, in the next video, actually finding the inverse. If we, have this formula, how can we find the inverse using algebra, okay, instead of just reasoning it out like we did in that first example.